Welcome guys to today's class. In today's video on practical physics, we want to discuss another aspect, another way of giving you experiment on simple pendulum. Yes, and that is why we call experiment on simple pendulum 2, because we have posted the first part where I showed you guys how to perform the experiment without touching apparatus, how to get your table of values, plot your graphs, answer your questions without touching apparatus. And if you want to still watch it, you just type Chidon's Daniel on YouTube. Just type Chidon's Daniel on YouTube. Then you see a lot of videos we have uploaded there. But if you want to go direct to the experiment, just type Chidon's Daniel experiment on simple pendulum. It will just show up immediately and you watch and enjoy. Okay? Also, in today's video, we want to see another aspect of experiment on simple pendulum. Remember that experiment on simple pendulum can come in many ways. You can perform it using a spring because it does move up, down. When you stretch a spring and release it, it will start moving up, down, up, down, up, down. We can use it to perform experiment on simple pendulum, oscillations up and down. You can also use the principle of cantilever. Cantilever simply means you have your meter rule, you clamp it on a desk or on something, on a wooden, maybe on a desk, wooden desk, anything. Clamp it somewhere, then displace the meter rule. Just displace it at a small angle. It will start moving up, down, up, down, up, down, till you get the number of oscillations you want to make use of. Here we are making use of 20 oscillations. Okay, so that is principle of cantilever, moving up, down, up, down, up, down. Are you getting it? Yes. Then you can use pendulum bulb, simple pendulum bulb, the one you tie the simple pendulum bulb on a thread, hang it, and you swing it at a small angle, and it start moving up, down, up, down, up, down, and you'll be counting your oscillations. So in this video, they have performed experiments on simple pendulum using cantilever, principle of cantilever, and they have given us the results they got. They are giving us the length, the time. They want us to what? Fill up this table. Now, to fill up this table, remember the self. If the relation between the period t and L is given by t square equal to a over b L cube, determine the value of a over b and state its SI unit. They want us to state SI unit, and so there is need for us to put everything in this table in SI unit format. Okay, now that means I will convert this length to be in meter, to be on a safer side, so that it will be easy for me to what? Get the SI unit, the exact SI unit as it's supposed to be. Because if I do not get or make use of SI units while doing everything, if I use this one that is not the SI unit of length, the implication is that after solving everything, I will start doing conversion. And if you make any silly mistake while doing the conversion, you have failed the question or you have failed the answer. And so there is need for us to package everything using SI unit, so that you will be able to get your exact answer, exact SI unit, and everything. Okay? Now, this is your T. How do you get your L in meter? Divide all the centimeter you are given by 100. Divide this by 100, you have 0.40, 0.50, 0.60, 0.70, 0.80, 0.90. We have divided everything by 100, so it is now in meter. We'll go for time. They are giving you this time. This small time is the time it took to get to a 20 oscillation. That is this small time given to us. So we say our period will be equal to small time all over number of oscillation. So we now say our period also is seconds. How do we get it? Divide all the t given to you by what? The number of oscillation given, that is 20. You have 4.5 divided by 20. That will be giving you in two decimal place 0.23. Okay? Then I will prefer as we have written it this, because we need t square, we use it as it is in calculator. You know, in calculator we have 0.225. Are you getting it? As the first value. And so we want it to be in two decimal place. That is why I wrote it like this. But if you have used the approximated result to be getting other ones, you'll be getting small higher digits, so to speak. So what you need to do is, once you approximate to this, still carry that 0.225, square it to get your t square. T square is second what square. Square it, you just say square immediately. It will give you 0.05 approximately. Okay, do the second one. 6.63 divided by 20, it will give you 0.3315. I will approximate to 0.33. I will have it as 0.33. I will now say square of what I got in that calculator. It will be giving me 0.11 approximately. Okay, I'm just using two decimal places to make everything uniform. Go to the next one. 8.25 divided by 20. I'll be having 0.4125. I'll approximate it to 0.41. I will square it as it is in the calculator. I'll be having 0.17. Okay, do the next one. 8.94, you divided by 20, you will be having 0.447. that is approximately 0.45. So you square it as it is in your calculator, you will be having approximately 0.20. You will go again. 10.88 divided by 20. The 20 is number of oscillation. You'll be having 0.544. You have 0.54. Square it as it is in the calculator. You'll be having 0.30 approximately. Okay, you go again. 11.83 divided by 20. You will be having 0.5915. So 0.59. So square it immediately. You will be having 0.35. We have gotten our t square, your t. Now to get your L cube, you say unit is meter cube. Okay, 0.4. The first one is 0.4 cube. You will be having 0.064. 0.5 cube. 0.5 cube is equal to 0.13. 0.13. This one 0.06 in two decimal place. We are just taking it in two decimal place. Okay, but if you are asked to put it in three decimal place, you obey the instruction. But I decided to use my own two decimal place. 0.6 cube. 0.22 in two decimal place. 0.7 cube. 0.34 in two decimal place, 0.8 cube, 0.51 in two decimal place, 0.9 cube, 0.73 in two decimal place. And so we have succeeded to get the table of value for this experiment. Now, it's important for you to note that they said if the relation between the period t and L is given by t square equals to a over b L cube, you just say t square equals to what? A over b L cube. Watch what it means. It means that when you make a over b subject to formula, L cube will come down. You have t square over L cube is equal to a over b. That means if you plot the graph of t square against L cube, if you plot the graph of t square against L cube, this will be automatically your slope. Are you getting it? You see, they didn't ask us to do the plot of graph of this, of that. But because they know that we are to deduce what we are to plot from what they gave to us, that is why they want us to do it by ourselves. And so that means if you plot the graph of t square against L cube, whatever you get as a slope becomes a over b. Obviously, the unit of the slope will now be second square over meter cube, because t square is second square, L cube is meter cube. Have it in your mind. That is the SI unit of the slope we are to get. Oh yeah, let's do the plotting. First thing you do, write the title of the graph. A graph of t square is second square against what? Against L cube in meter cube. Then write the date. Write the date, write the title. They have their own mark. Then we now say that when you are given this problem to solve, you are considering t square and L cube now. T square and L cube. Okay. Choose your what? Scale. To choose it, okay, let's label our what as this. This is t square in second what? Squared. And this is L cube in meter what? Cube. It's not a must that you start it this way. It depends on the nature of the readings you have. Now, watch. On our channel, in that Chidon's Daniel I just wrote before now, you will see where I discuss how to choose appropriate scale. How to choose appropriate scale. And so, I may not continue doing it in this video because of time. Are you getting it? Now, this is t squared. The highest is 0.35 and the lowest is 0.05. I will not be writing how to choose it anymore. Watch it. If I write 0.0 here, right? Here, 0.05, 0.1, 0.15, 0.2, 0.25, 0.3, and 0.35. That means it can enter by using 0.0. Then here the highest is 0.06 and the lowest is 0.06 and the highest is 0.73. What you do, okay, let's say 1, 2, 3, 4, 5, 6, 7, 8. 6 times 8. Will it go? No. Okay, let's check. If here is 0, you know when you write 0.0, it means that this second one is talking about your y-axis. And so this is 0, 0.05, 0.10, 0.15, 0.20, 0.25, 0.30, and 0.35. So it entered the t square own. Coming to what? The horizontal. We have sorted out this one. This is your y and this is your x. Coming to this, if here should start with 0, the question is, can we achieve scale that will accommodate 0.6 to 0.73? That is the question. Okay, let's check. If I write 0 here now, I can say here 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7. Think it can go. So I write here 0.10, 0.20, 0.30, 0.40, 0.50, 0.50, 0.60, 0.70. So we are saying the concept of you choosing appropriate scale is just to choose a good number that can accommodate the values you have on your data, such that the difference between this and this will be equal to this and this will be equal to this and this will be equal to this and this. So you have to have that information. Then plotting, now we have 0.05 against 0.06. 0.06 should be between 0 and 0.1. So we can take care to be 0.06. It should be more than the half. So we go again, 0.11 against 0.13. 0.11, remember this is not the standard graph, it's just a sketch of the graph. And so you use your standard graph to do your own plotting and tell us what you got. 0.11 against 0.13. You would say here 0.11 is against, then 0.17 against 0.22, 0.17 against 0.22, 0.20 against 0.34, 20 against 0.34, 0.30 against 0.51, 0.51, 0.35 against 0.73. Are you getting it? We have located our what? Points. We have located our point. Next is for us to get our line of best fit. Next is for us to get our line of best fit. For you to get your actual line of best fit, please get the mean of your L cube and mean of your T square. Let's get their mean. 0.06 plus 0.13 plus 0.22 plus 0.34 plus 0.51 plus 0.73. Then divided by 1, 2, 3, 4, 5, 6 divided by 6. We'll be having 0.33. So the mean of this is 0.33. Let's check T square. 0.05 plus 0.11 plus 0.17 plus 0.20 plus 0.30 plus 0.35 divided by 1, 2, 3, 4, 5, 6. 0.2, 0.19, 0.197, 0.197, or approximately 0.2, whichever one. Okay, let's plot 0.2 against 0.33 against 0.33. Look at 0.2 against 0.33 is somewhere here. Is about that 0.2 against 0.34. It will be there. That means the line of best fit must pass through here. It must pass through here. through the centroid. We call this mid of this and main of the where they meet. We call where they meet the centroid. So the line of best fit must pass through that centroid. Okay? Wow, we are done with the word line of best fit. If you check this line of best fit, it might not be what you have in your mind before now about line of best fit. I know that a good number of persons have this mentality that line of best fit simply means that the line will pass through all the points. No, no, that mentality is poor. Line of best fit simply means a line that will pass through the centroid and be able to also pass through other points such that the points that will fall out will fall on different sides equally. Look at this line of best fit. 2 points fell out, whereas 2 points fell out on the other side. We say this is a good graph plotting or a good way of locating line of best fit, because you've seen that if you check it well, you will notice that 2 fall out this side and 2 fall out the other side. Only this point here with the centroid and with this point, only the 2 points entered. And so this is our line of best fit. Then to calculate the value of A over B, we need to get the slope of this curve. To get the slope, we say draw a vertical line from any point such as this point. Then draw a horizontal point such as this one. Are you getting it? We call here change in t square and we call here change in L cube. Now let's check here. What is the value for this point? To get the value, we can say this minus this is 0.05 divided by 10. So let's say that this is 0.25, 0.26, 0.26, 0.27, 0.28, 0.29, 0.3. So we can take here to be 0.29. We say 0.29 minus, check here, 0.10. Then coming to L cube, we take here to be 0.60. We take it to be 0.60 minus, we take here to be what? Here is 0.06. 0.06. And so when you get to this point, you use your calculator. Now, we say slope equals to 0. Equals to change in t square all over change in L cube, and is equals to 0.29 minus 0.10 all over 0.60 minus 0.06. Let's check what it will give us. 0.29 minus 0.10 divided by bracket 0.60 minus 0.06. So that will be giving us 0.35. 0.35. What is the SI unit? SI unit is what? Second squared all over meter cube. Yes. You see, it's easy for us to get the SI unit because we made use of SI unit from the starting point of this. And so when you are done with this, don't forget to include your scale, the scale you use. For t square axis, tell them that 2 cm is equals to what? This minus 0.05, 0.05 second squared. Don't say 0.05 units, say 0.05 second square. Then in L cube as is, we say 2cm is equals to, this is L cube. Are you getting it? It's equal to this minus this, 0.1 meter watt cube. Remember, I said this is just a sketch of a graph. So try to use your own standard graph and what? Do the plotting, do your what? Slope, and tell us what you get. That means since our slope, we said our slope is t square over what? L cube. Since our slope is t square over L cube, we say that whatever we get as our slope is equivalent to A over B. Is equivalent to A over B. And so we will say that A over B automatically is equal to 0.35 second square over meter cube. 0.35 second square over meter cube. That is for this experiment. Now they say calculate the standard error in A over B. There are numerous ways. There are many ways you can use to get the standard error. Please also type Chidon's Daniel ways of getting error in slope. Type it on YouTube. Chidon's Daniel ways of getting error in slope. You will see all the possible ways. I talk about 2 possible ways you can use to get error in the slope. Just type Chidon's Daniel. I've given the spelling before now. CHY. Chidon's Daniel ways of what? Finding error in the slope. You will see the video and you will watch. Okay? As you watch, feel free to click subscribe and like the video, share to your friends, comment so that we'll keep learning. Okay? Now, I will use one of the methods I discussed in that video to apply it here. I will just apply one of that method. And one of that method means the principle of worst fit, slope of worst fit, and slope of what? Best fit. Use of the principle of slope of worst fit and slope of best fit. I will use it here. Let's see how to use it. We take this slope we just drew. We take it to be the slope of line of best fit. Are you getting it? So we will call it BF, best fit. Now to get the one of worst fit, I will connect the one that fall out. I will connect the points that fall out, or one of the points that fall out, or 2 of the points that fall out, depending which one is possible. So I will connect it to the centroid and get my line of worst fit. Let's get it. Wow, so this one can go. We take it, take it, take it. Okay. Okay. We are done with this line of what? Worst fit by connecting this, this, and what? This. Okay. We have gotten that. Now, what we are to do is we get the slope of this line of worst fit. Let's get the slope. We draw from here. And we draw from here too. Okay. Change in L cube for this one is equals to, what do we have? We take it from here. We say 0.50 minus, here is where it meets, and we call it 0.06. Are you getting it? just from here to here, from this point to this point. Are you getting it? You noting it? Then for this one, here is we'll take it to still be 0.29, 0.29 minus here 0.05, 0.05. Eh. So we have gotten this 0.29, we have gotten the lowest value 0.05, we have gotten this one 0.05, and we have gotten this one 0.06. Then we get this slope as well. We say worst fit slope. Worst fit slope is equals to 0.29 minus 0.05 all over 0.50 minus 0.06. Let's see what it will give us. 0.29 minus 0.05 divided bracket 0.5 minus 0.06. So we'll be having it to be 0.55 second square over what? Meter cube. Recall that when we did the first one we call here 0.29, the second one minus 0.10, then this one 0.6 minus what? 0.06, and we got 0.35, right? Okay. Then for the worst fit, we said that here is 0.29, this point that it is 0.29, we take it down to what? 0.05. Okay. Then we also said 0.05, we take this one down to 0.06, and so it gave us this. Now, how do you get your error in slope? Standard error in slope is the difference between 0.55 and 0.35 you got. From this modulus means if you say the best fit minus the worst fit, you must still put modulus to show that the answer must be positive. If you also said the worst fit minus best fit, you must still put modulus to show that the answer must be positive. Remember, we said this is just the sketch of the graph. Sketch. Are you getting it? You might plot it using standard graph and you see that it's not the exact value, but this video will help you to see how to follow it up and get the actual value. And so this minus this 0.55 minus 0.35, that will be giving you 0.2 seconds square per meter cube. That is the error in that slope. Are you getting it? The error in the slope is 0.2. A lot of things can cause a particular error gotten to be high. That is when we talk about precision and accuracy. How accurate you were while getting the values you use in graph plotting. If you are very much accurate, that is, you are able to stop your pause your stopwatch at 20 oscillation immediately. Some persons, while trying to pause the stopwatch, it has even reached 25 because they were exhibiting Parkinson. Their hand was shaking while trying to stop the stopwatch. Are you getting it? So if you're able to get the stopwatch pause at 20 oscillation dot, you will get a higher accurate answer and your error will be very very small. But if you are not able to what stop it at exactly 20, maybe you stop it below 20 or above 20 oscillation, that means you will likely get a higher what error in what you perform. So this is a way you have to follow to do this experiment. So in every experiment you perform, whether they ask you or not, try to include the precautions you took note of while performing that experiment, so that it will show you know what you are doing. Yes, you know, one of the precautions in simple pendulum experiment is ensure that while displacing the meter rule, you displace it at a small angle. Look at what I mean. Look at this meter rule. If I'm to perform the oscillation, I have to display it small so that it will just be moving 1, 2, 3, 4, 5, 6. But when I displace it higher, it will be moving faster. You will now see that by the time you are trying to pause it at 20, you will notice that the thing have even reached 25 or more than. And so there is need for you to display it as a very small angle. Take note of parallel error while making use of your meter rule to take a measurement, or while using the stopwatch to take a measurement. Note all this, very important. So ensure you include your precautions after performing your experiment. You will see more videos on our channel, Practical Physics. Yes, please, if you enjoy our videos, feel free to click subscribe. It will not take you any dime. Also, share to your friends, comment, like the video. See you next time.